What is angular position, angular velocity, and angular acceleration? So we're talking about things that goes in a circle, spins around. For example, you go to there, you take your nephew, you go to the merry-go-round. And that thing, you go on the right, and you go in a circle there the whole time. You're on that little horse that's going around the circle. So your distance here, it's not measured in meter. It's measured actually in radian. So for angular position, we measure the distance because you're going around a track there. We actually use theta for that. And the unit for that, rad per second, or radian per second. Oh, rad, not rad per second, I'm sorry. I need to wake up today. The distance measured in radian. Radian per second is the speed. So your distance measured in radian. So for example, you're on the merry-go-round here, and you did 10 turns. Can you tell me what your theta is, or your angular position? How far did you travel? I have to give you one more thing about this problem, is what was the radius? What was that radius there of that track there? Let's say the radius is 5 meters. And you're on this edge and you went around here 10 times, 10 turns, 10 revolutions. How far did you travel? Okay. 1 revolution is equal to what, Jason? You said the pi. 1 revolution is what? Just 2 pi? In radian, that's 2 pi. Yep. 2 pi r in meters, right? Yep. So 2 pi, 1 revolution is 2 pi. So if you do 10 turns, then how far do you travel? 10 revolution will be what? That's over 1. Each revolution equals what? 2 pi. So 1 revolution is 2 pi here. And if you cross the revs here, you travel how far? 20 pi radian. That's how far you went. Now, I gave you R here for a reason there. If I asked you distance-wise, if you were walking on the street, how far did you walk? Or if that's the wheel of your bicycle, you're on your bike, and well, that's a huge bike, 5-meter radius. That's the size of the height of 2 buildings, 3 buildings. But if you were on that giant bike, and the wheel made 10 turns here, how far did you walk? That's x, the distance, that's the linear distance. On the ground. Or another way of looking at it, if that was a tape attached to the wheel and it came loose, and as the wheel is turning, that tape is just sitting on the ground, can you measure the length of that distance? This will be a good example of it. This paper here. This paper, that's the wheel of that bike. And it came loose, notice? And as you're moving, you can see that paper is laying on the ground. So if this one turns 10 times, how long is that piece of paper on the ground? What's the length of it? How do we figure what that is? Well, let's look at one turn right here. I don't know if you can see on this one. When you do one turn from here to here, there's the length of it. Let's cut it right there. What's the length of that paper? Isn't that the circumference of the circle? And the circumference of a circle is what? Isn't that 2 pi times r? So one revolution, if you want to find the distance, it has a circumference c of 2 pi times r. That's the distance. So if you do 10 revolution, what's the distance that you traveled? The distance that you travel, it's 10 times c, which is what? 20 pi times r. This is in meters. Notice here, this is your distance in theta, and this is your distance in x in meters. Look at the two numbers, very similar to each other. What do you notice the difference between them? That to give the distance in meter, you take your distance theta and you multiply it by what? R. So that's really the relationship between linear versus angular position. X is always equal to R times theta. I wanted to derive that equation. So if you know what your angular distance is, you know what your linear distance is R times theta. And make sure theta is in radian, not in degrees. With all these homework assignments in this chapter, you better make sure you calculate in radian mode. So if you want to do that now so you don't forget, Jason, put in radian. And there's a button on it, it's probably said DEG, RAD, and you can switch. On the TI 83, 84, 85, you can go to settings and you can see it there.
You said DEG.
If you click on it, it's with DEG, RAD, a button there.
DRG.
DRG.
Mine says DRG.
So if you hit it a couple of times, we'll switch from one to the next to the next. It's radian, degrees, and gradient.
So if it's on degree,
If it says DEG, that's in degree mode.
so then click the radian.
So this calculator, actually the one you have, Jason, notice has a mode on the top. I can't read it, but if I zoom in on it, I can't zoom in when I'm recording, but if you zoom in, it says to change it to that mode, and you can switch. I don't know if anyone can see it, degree and radian there. But that allows you to switch between degrees and radian, which mode. Here we go, RAD. And I think it says, I don't know what that number is, 6 or 5, or couldn't even tell you.
Yeah, it's 5. So I hit shift, mode, 5. Yeah, it says rad.
Yep.
Okay.
So shift mode 5, shift mode 5, and notice it's rad. Shift mode probably 4, that's degree. So you go back and forth between degrees and radian. Depends on what kind of calculator you got there. If you got the TI 83, you guys figure that out. You go to settings or mode. Thank you. Yeah, go to mode, and you will see radian degrees switch to radian. But there is a relationship between how far you traveled, how many turns you made, and R. The bigger R is, the longer the distance. If you do 10 turns on a bigger wheel, you're going to travel much farther than if you did only 10 turns on a small wheel. So when things are spinning, we measure the distance in theta, but there's also a relationship between the distance on the ground versus how fast you're turning. And that's this relationship. That's your linear speed. Again, think about it if you're on a ski lift, or you're riding your bike and you're pedaling, you know? Your bike is going on the ground. That distance you're covering on the ground depends on two things. It depends on R, how big the radius of the wheel on your bicycle. Is it 25-inch wheel, 26, 27? How big your bike? And also theta. How many turns did you make? If you travel 10 turns, 10 turns multiplied by R, that will tell you the distance on the ground. In speed here, or velocity, for angular velocity, we use W. If you remember, linear speed, what did we use? What was the unit for speed? Or what letter we used? Then we use V, which is what? meters per second, right? For angular speed or velocity, we use W. And that's, instead of meters per second, that's distance divided by time. The distance measured in radian, the time is measured in second, radian per second. Now, one little problem here with distance and speed. If you remember, when you travel to the right, we said that's a positive distance. When you go to the left, that's a negative distance, right? And speed, the same thing. How do you know if the distance is positive or negative? What do we use? Exactly, clockwise and counterclockwise. If you do counterclockwise, your distance theta is positive. So let me put that here. Counterclockwise rotation it doesn't look like clock here. I don't know, I wasn't looking. Oh boy, he's trying to squeeze it there. Counterclockwise, theta is positive. Clockwise, theta is negative. So if you're going clockwise, theta is negative. If you're going counterclockwise, theta is positive. And the reason, if you think about it, the reason for that, when we're doing trig there, if you travel this way, that was a positive theta. But if you travel this way, that was what? Negative. We measure the angle that way as negative. And we're still using the same thing. Counterclockwise, that's positive theta, but if you're traveling this way, that's a negative theta. The distance is negative. With the speed, the same thing. W, we said we use in radian per second, and it's the same thing. If it is counterclockwise, that's positive. W is positive, greater than 0. And clockwise, W is negative. Just like there's a relationship between your linear distance and angular position there's a relationship between linear speed and angular speed. Your linear speed, V equals R times W. How fast things are spinning is related to how fast you're moving on the ground. True story. Probably my son was born in 1991. So probably 1989. I'm coming from the beach at the Cape at night, 1 o'clock, 2 o'clock in the morning, driving my Vet, Chevy Chevette. Probably don't know what that car even. That car couldn't even go 70 miles per hour downhill if you pushed it. But I got pulled over by the state police going, you going 70 miles per hour. Keep in mind the speed limit was 55. I'm arguing with the cop. I wasn't going 70 miles per hour. I was going 65. I set my cruise control. It did have the cruise control. You going 70. Now at 2 o'clock in the morning, he had me outside the car, my hands on the top of the car, because I'm arguing, I'm stubborn. And my officer says, just take the ticket. Finally, my wife talked me into taking the ticket and just shut my mouth and go home. So I got the ticket and I came home. That time was $50 ticket, 1980 something. That ticket probably is about $300-400 today, inflation. But anyway, I'm still like steaming. I know I was not going 70. So I get on the highway and I get my wife driving next to me, and I go, okay, I'm going 65. No cell phone, keep in mind, roll the windows. How fast am I going? She goes, 70. Let's try again. 65. I said that girl, how fast I'm going? She goes, 70. She's next to me with her car. Then it hit me. I bought new tires. And the guy said to me, I got these cheap tires, somebody returned them, they're bigger size, a little bit bigger. If you want them, I'll give them to you for a couple of $100 on your car. I'll put them in. I said, sure, what difference does it make? And it does make a difference how fast you're going, because the RPM is telling you how fast the tire is rotating, how fast it's spinning. Well, just think about it. If your W, you just take a number, pick a number, any number. 7 or 70? 70, okay. 70 rad per second. And let's pick a value for R. Pick a number for R, any number you want to use. 15. What is V equal to here? R times W. 15 times 70. What's 15 times 70? 1050. If this is probably, let's say, centimeter here, this will be centimeters per second, which is 10.5 meters per second. Now what will happen if W stayed the same? And that's what happened to me on my car. And let's say R equals 17 centimeters. We got one couple of centimeters bigger. What's my velocity now? It's R times W, which is 17 times 70. And I'm going now 1190 centimeters per second. So I went from meters per second. I went from 10.50 meters per second to 11.9 meters per second. In miles per hour, 10.50 times 2.24. My speed was here 23.52 miles per hour. It went to 11.9 times 2.24. It went to what? 26.7 miles per hour. So by just keeping W the same, just increase the radius by a few centimeters now, my speed, I'm 3-4 miles per hour faster than when I was going. So your speed, your linear speed, how fast I'm moving on the road, it depends on two things. How big R is and how fast the wheel is spinning. What is W? If W increases now, even with R the same, I'm going to be going faster. So imagine now if your RPM here, you're not going at 70 rad per second. Now again, your RPM in your car, if you're driving, probably what, 3,000? Normal car? What's W? If the RPM is 3,000, can you tell me what W is? So my car is spinning, my RPM in my car says 3,000. What does RPM stands for? Anyone? Revolution per minute. That's your speed. That's your W, but it's not in the right units. We don't like RPMs. Can I change that number to rad per second? I go 3,000. It says revolution per minute. Now let's take revolution here and change it to radian. One revolution has how many radian? 2 pi. Now minutes on the bottom, I need minutes on the top and seconds on the bottom. 1 minute has how many seconds? 60. And notice now this rev cancels that revolution. This minute cancels that minute. And my units are rad per second. So 3,000 times 2 pi. Where's pi here? I know there's pi somewhere on this calculator. Can't see it. Oh, big button right there. Divided by 60. So my RP or my W here is really 314 rad per second. So imagine now if you go back to that problem, instead of 70 rad per second, you put 314 rad per second. 1 centimeter and change in that will give you over 5-6 miles per hour easily. And that's what happened to me. My car is spinning at a speed of 314 rad per second. You go from 15 centimeter to 16 centimeter, and you'll see the difference in speed.
Why didn't the speed in your car tell you that you're going 70?
Because it goes by the RPM, I mean how fast the wheel's spinning, not the distance on the ground. That speedometer tells you, it counts how many spins you spin there. So it's based on that.
Mechanics would have to adjust the ratio. Very sophisticated back then.
So again, there's a relationship between the linear speed and the angular speed, and that is the relationship. So, okay, what about acceleration? Let's look at the third piece, angular acceleration. Now, linear acceleration, we use what letter for linear acceleration? We use the letter A. For angular acceleration, we use a Greek letter. It looks like it's called alpha. Looks like a fish. Alpha. For linear acceleration, the units are what? Meters per second squared. Here, what? Rad per second squared. And just like the other one, there is a relationship between the linear and the angular acceleration. A equals r times alpha. If we know what your angular acceleration is, we can tell you what your linear acceleration if we know what r is. If we know two of these, we can tell you what the third one is. So they're all the same thing. So basically, a summary here. For distance, when things are spinning, go in circle, we use what? Theta to measure the distance. For speed, velocity, we use what? W. And for acceleration, what do we use? Alpha. This is the linear here. This is the angular. And every one of them related to the other one. X equals r times theta. V equals r times W. A equals r times alpha. That's really the summary of this section. Angular versus linear. We use angular when things are spinning in a circle. Bicycle wheels. the wheels on your car, the drill when you go to the dentist. That beautiful sound, zzz, 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 you know, everyone loves to hear. That spins in a circle there. That's angular speed, angular distance, angular acceleration. Okay, let's take some examples and see how we're going to use that. Rotational kinematics. Things are moving but in a circular path. That's the next section.